Before going to the second module, we should know the velocity triangle for Pelton turbine, reaction turbines, steam turbine, Parsons reaction turbine, all those things you should come to know. So that the very first sheet I shared this. D-level turbine velocity triangle looks like this. Parsons turbine velocity triangle looks like this. Pelton turbine inlet and outlet looks like this. And Francis and Kaplan turbine looks like this. High speed, medium speed, and low speed. Okay, for this, for this module, you should be very thorough with the velocity triangles of various modules. And outlet triangle for the Francis turbine, whatever may be the speed, it remains same as this. Coming to the centrifugal pump. Okay, centrifugal pump, inlet is important here. In the centrifugal pump, inlet is not so important. So that inlet triangle is like this, but outlet looks like this. Okay, so in the centrifugal pump, outlet is important for us. In the Francis turbine, inlet is important for us. Okay, then coming to the energy transfer, energy exchange, or energy transfer through the turbomachine. In this module, they will ask an important question is Euler's turbine equation. What do you mean by this Euler's turbine equation? All the module we started with the Euler's turbine equation. Remember, E or work done is equal to U1 VU1 plus or minus U2 VU2. That is called as Euler's turbine equation. So here we'll come to know how that derivation or how that expression came. Okay, it is a basic and the general relationship equation applied for all the turbomachine. This is obtained from Newton's second law of motion. Okay, applied for the any rotor. So these are all the assumptions. Mass flow rate is constant, steady flow, leakage loss is negligible, the rate of flow at which the energy transfer takes place, all these are negligible. Here you can see the brackets, and this is nothing but what are all the things you should write first. If we ask you to derive the Euler's turbine equation, you should draw this first. Means first you should write this one, definition of the Euler's turbine equation. Then you go for the assumptions. Then you don't start with this. You go with the figure. You're supposed to draw the figure. That is the third step. And the fourth step, you're supposed to write this. Okay, means in the figure what it tells, what is the point 1, point 2, all those things. This is the fourth step. And this is the fifth step you're supposed to do. What is that? This is the fifth step. After this, you write this as a fifth step. Okay. Then you go for the sixth step. This is the sixth, seventh, then till here eighth. That up to here you're supposed to do. However you write there, accept that. But if you may follow this procedure or flow, what I written here, then it will be properly represented. Okay. What it is showing here, you take any rotor, and then at the center of the rotor you fix up the shaft. Assume that water enters at a point 1, or any fluid enters at a point 1 in random direction and leaves at point 2 at some random direction. So because of this, assume that this rotor starts rotating because of hitting of this V1. Rotor starts rotating at an angular velocity of omega. Omega is the angular velocity. Here I given 1 is the inlet point where the fluid enters. Point 2 indicates the outlet point where the fluid leaves the rotor. And R1 is the radius at which the fluid enters. R2 is the radius at which fluid leaves the rotor. Only you can see, literally you can see V1 and V2, which is entering and which is leaving. But because of these two, there are 3 mutually perpendicular reaction forces will be generated. That is VA, VU and VR, or it is also called as VM, or which is also called as VF. So which are perpendicular to each other, these forces are created. See, because of one, how to draw this figure? Draw the line which is parallel to V1. Then from here, draw the line which is perpendicular to the axis of the shaft, and draw one line which is perpendicular to the axis of the shaft from the base, and one is which is parallel, that is VA, should be parallel to the shaft. Like that you're supposed to draw. One is perpendicular, VU is also perpendicular from the base, and one is towards the axis. Means this should follow, or this line should be parallel to the axis. Like that you try to draw for the inlet as well as the outlet. And the naming also you should concentrate. So what will happen here? You're supposed to find out the force. Or else, okay, instead of force, first beginning what we can say is V. Because of V, once the fluid is entering, that is V1 or V2, 3 forces will be created, as you've seen in the figure. That is VA, VR and VU. Here I cancelled off VR and VA because I written here the reason. VA is the axial component which is parallel to the axis. VR is the radial component, which is radius of rotation, which is parallel to the radius of rotation. VU is a tangential component, which is tangent to the axis. That means what will happen? This VR will try to push the shaft. It will not try to, or it will not contribute anything for the rotation of the shaft. So this will be this. It is nowhere used for the rotation of the blades. Thus VA, the force because of V1, VA is created. That VA is created parallel to the shaft. That will also nowhere act to the rotation of the wheel. But VU, which is created here, that is tangent to the rotor. This should be tangent to the rotor, and that will create a rotary motion of the rotor. So that V1, whatever the V1 value is there, it is a combination of VM or VR or V and VA, VU. These three are the combination. If I add up these three velocities, I'll get V1. It is sure. If I add up VR, VA, and VU1, I will get V1 value. But VR, this velocity and this velocity is wasted because this is nowhere. These two velocities are nowhere contributing for the rotation of the rotor. Only the velocity which is contributing to the rotor velocity is, our rotor motion is VU. So that we have to consider VU. As far as possible, whatever the V is there, if you make this VU1 length more, means that is equal to V1, then it indicates the velocity of the rotor, the efficiency of this turbine is good. Because this should be minimum and this should be minimum. Only we should concentrate more on this VU1 should be equal to V1, then only our efficiency of the rotor is greater. Okay, so that I written this equation. V is a combination or addition of VA, VR, and VU. If these two are nowhere contributing for the rotation of the rotor, and if I want a maximum, then V I can write as VU. Okay. Similarly, force. What is the force equation? Force is equal to mass into acceleration. Mass is m, acceleration is v by t. So where I taken t at one side, m by t into v. M by t I can rewrite as m dot into v. That is m dot v1 minus v2. So m dot into dv. So what is v1? As per this equation, v1 is nothing but a combination of these three. But if I cancel off these two, v1 will be equal to vu1. So that m dot vu1 minus of vu2. So the forces acting on the rotor is this. This is the force acting on the rotor. In any rotor you may take, is the force acting. Similarly, torque, force into distance. M dot vu1 is acting at a distance of r1 and vu2 is acting at a distance of r2. Similarly, the rate of energy transfer, E is equal to m dot vu1 r1 omega 1 and omega 2. These are all the basics you know. And the energy transfer per unit mass flow rate of the fluid is cap E dot divided by m dot. E dot by m dot, I can call it as a small e, that is Euler's turbine equation. What is remaining? If I take the m dot outside, I'll get only u1 vu1 and u2 vu2. So this is called as Euler's turbine equation. Small e is Euler's turbine equation, u1 vu1 and u2 vu2. How we got this? So what is the unit for this? Meter square per second square, joules per kg. I can write the unit for this as meter square per second square or joules per kg. That is called as Euler's turbine equation. Remember, small e or w is called as Euler's turbine equation. Okay, and then here I written a note. This is important. If the value of u2 means u2 vu2 is nothing but outlet energy and u1 vu1 is inlet energy. For a turbine, inlet energy should be greater and outlet should be less, correct? If I want to maximum efficiency of the turbine, the energy given to the turbine should be more and outlet from the turbine should be less. So that VU1 U1 should be greater than U2 VU2. So that's what I written here. U1 VU1 should be greater than U2 VU2 for the turbines. But for the pumps and all, inlet energy will be less, but outlet energy will be greater. So that the value of U2 VU2 will be greater compared to U1 VU1. For power absorbing machine, see pump, what will happen? Inlet energy for the pump is less. That is U1 VU1 should be less compared to U2 VU2. Compressor, blower, you take any power absorbing machines, U2 VU2 should be greater than U1 VU1. But for turbines, it should be reversed. Inlet energy should be greater than outlet energy. Okay. Then they will ask what are the three velocity components. You saw no VA, which is perpendicular to V1, VM or VR. This is also perpendicular to V. VU is also perpendicular component. This is called this is a tangential component. And VA is an axial velocity component. It is given here. This is parallel to the axis and produces no rotation of the rotor. And VR is also radius radial force produced due to the change in the magnitude of the force is taken as external bearing. So this is also waste of energy for us. Very important energy which is only contributing for the rotation of the rotor is tangential component. This is the tangent to the rotor of the radius. Torque is exerted on the rotor due to the change in momentum of the component. So these three are the component where we will get from V. That is absolute velocity is V1. From the V1, these three components, perpendicular components will come, where this is parallel to the rotor. This is this is perpendicular to the shaft. This is parallel to the shaft, and this is tangent to the shaft. So these two is wasted because they are acting perpendicular and parallel to the shaft. There is no use for rotation of the blades. Only the rotation or the rotor will be rotated with the help of this tangential component. So as far as possible, we should make this VU or tangential component should be greater so that the rotor will rotate at higher speed. Okay. This is one equation what he is going to ask many times. He has asked this figure and follow as per the steps so that it will be in proper order. So that is one thing. The second thing he is going to ask in this question is modified Euler's turbine equation. I'll show you that. What is that modified Euler's turbine equation? That also a project I have given in the notes. Yeah. So many times this is asked. Many times you may consider probably this will come for the exam. Okay. So what you studied is a Euler's turbine equation, and other Euler's turbine equation is that is called as a modified Euler's turbine equation. Here for your reference, I given few years where he has asked. He has asked plenty of times. Okay, more than 10 to 12 times he has asked. More than 12 times he has asked. Okay, from once the VT is converted to means from the Bangalore from the Coimbatore University it is converted. So sorry, whenever the VT has started, no, from there if you check out 10 to 12 times this question is asked, so that you concentrate more on this. Derive an alternate or a modified. You can ask as an alternate form or a modified forms of Euler's turbine equation with the usual notation. You can ask like this, or you can also ask like this. Draw the velocity triangle at inlet and outlet of turbomachine in general and show that the energy transfer per unit mass is given by some equation will be there. I missed it. That you can we will find out at the end whatever we get that he has to write here. Okay, let us consider the generalized velocity triangle. We will not consider inlet is perpendicular or horizontal or tangential. We will leave that. Just we will draw an inlet velocity triangle randomly and outlet triangle also randomly in this manner. Okay, you draw this U, VU1, U2, VU2, all those things I satisfied here. Okay. So what is V1? Those things you should write here. Absolute velocity of the fluid. If I put 1, you put inlet absolute velocity. If I put 2, you put absolute velocity of the fluid at the outlet. So like that, you write the notation for all those things, what is there in the velocity triangle. Then, by considering the velocity triangle OBC, you see here, where is O, B, and C? If we consider this triangle, I'll come into picture regarding VF2, V2, VU2, and alpha 2, right? So consider the outlet, consider the triangle OBC. From the outlet triangle OAC, that is OAC. So we will consider OBC once and OAC once. In this, if you consider these two triangles, which is common term, that is VF2 is common term, right? So let us express VF2 with respect to OBC and OAC and equate those two. We'll get one unknown. See here. Just a minute. I'll download it. So this is very, very important question where so many times this is asked. Yeah, the same thing it is there in the Google Classroom also. See, by considering OBC, VF2 square is equal to V2 square minus VU2 square. You can see VF2 square is equal to V2 square minus VU2 square. Similarly, considering OEC, you can write VF2 square is equal to VR2 square minus VU2 plus U2 square. Okay, this is our value I written. After simplifying, I'll get VF2 like this, and VF2 I got that. Let us put this as 2.4 and let us put this as 2.5. If I equate that, compare, means if I equate this V of 2 square and in both 2.4 and 2.5, what will happen? V2 square minus VU2 square, that will be equal to this, right? Go on simplifying so that I'll get VU2 VU2 in the form of half into V2 square U2 square VR2 square. Similarly, from the inlet triangle, if I do, I will get U1 VU1 in this form. U2 VU2 we got in this form, and U1 VU1 we got in this form. Let us put these two values in Euler's equation. What is the standard Euler's equation? E is equal to U1 VU1 plus or minus U2 VU2. So we know V1 VU1 is this, U2 VU2 is this. So let us put in the Euler's turbine equation. And that's what it is written here. Substituting the equation 2.6 and 2.7 in Euler's turbine equation. That in my textbook it is 2.2 and 2.3. So I written here. So you know Euler's turbine equation, right? It is E is equal to, just now we discussed, VU1 VU2 plus or minus U2 VU2. So if you substitute that, then the Euler's turbine equation will become like this. For power generating machine and for power absorbing machine, this will become. So plenty of times this question is asked, modified Euler's turbine equation. So in this, if I divide this, means if I divide this and this into three headings, I can write as first component, second component, and third component. What is the first component? V1 square minus V2 square by 2 for power generating machine, and for power absorbing machine, V2 square minus V1 square by 2. So what it indicates? It indicates change in absolute kinetic energy, and which causes a change in dynamic head or dynamic pressure of the fluid through the machine. Similarly, second component is this. Third component is this one. So you should be very, very careful while writing these three components. See, what the question they will ask is, derive the modified Euler's turbine equation and explain the three different components. First component, second component, and third component. First component tells about absolute kinetic energy. Because of this absolute kinetic energy, dynamic head or dynamic pressure of the fluid changes. Second component is centrifugal energy. Because of this, radius of rotation of the fluid will take place. Rotation of the fluid will take place. And third component is change in relative kinetic energy, which causes the change in static head or static pressure. That is very, very important. Is it clear? Okay, I hope that you can follow this modified Euler's turbine equation from the Google Classroom. You practice that plenty. You practice 100 times. It will help you a lot. That modified Euler's turbine equation is very, very important for the exam point of view. Are you getting? Srivatsan, Vijay, are you getting?
Yes, sir.
So I shared the notes of that Euler's turbine equation, modified Euler's turbine equation, and all the notes, entire notes of the second module in the Google Classroom. Please go through and then prepare well. Any doubts in the modified Euler's turbine equation? Srivatsan, Vijay?
No.
Okay, you please go through that. Okay, then I'll go for the next heading. What they probably ask. See, for you too, I tell definitely if you prepare this modified Euler's turbine equation, it will help you a lot to score good marks. Definite question in exam. You can write a note somewhere. You can make a note somewhere. It is a 100% question. Most of the time they've asked. Okay. This is called Euler's turbine equation, as I explained earlier. And the other one is modified Euler's turbine equation. Then he'll ask the question regarding this. Degree of reaction. What do you mean by the degree of reaction? These are all only half-page derivations. There is not much. If you understood that modified Euler's turbine equation, you can derive this easily. See here, it tells about the efficiency and hence selection of the turbine based on this degree of reaction. That means the other way you can define like this. It is the ratio of energy transfer due to the static pressure change to the total energy transfer due to the total pressure change in the rotor. It is R is equal to, you can write like this, static head, total head. What is the static head? Just now we did in the modified Euler's turbine equation. We did this, right? Just a minute, I'll show you. Here in the modified Euler's turbine equation, we got here static head. This is absolute kinetic energy, centrifugal energy, and static pressure. See here, this is called static head. So what is the degree of reaction tells? This degree of reaction tells static head divided by static plus dynamic head. So out of these three, which is the static head? So this is static head. Just I'll highlight this. Static head. This is called dynamic head. And this is called again static head. Okay. So these two are static head and this is a dynamic head. So you put these two formulas, that is this in terms of V1, V2 and U1, U2, VR1, VR2 in the equation of degree of reaction. See here, what he has done, very simple. Static head, I'll show this in other screen. Can you see both the screens here?
Yes, sir.
See here. Static head, where is the static head in this? This is static head, this is static head. So what is the degree of reaction tells? It is a ratio of static by total head. That is static by static plus dynamic head. What is the static head? U1 square minus U2 square plus VR1 square minus VR2 square. That's what I written here. U1 square minus U2 square plus VR2 square minus VR1 square is called as static head. And dynamic head, it is given here. V1 square minus V2 square by 2. That is dynamic head. So using these, how we got the static head and dynamic head? We got from modified Euler's turbine equation. From this, you take and place here in the equation of degree of reaction. If you place now, what will happen? R is equal to, if you simplify, this R will convert into only this formula. This R is simplified in this form. That is Euler's turbine equation minus of half into V1 square minus V2 square divided by Euler's turbine equation. This is called degree of reaction. Many times this also asked. See, there are few questions in this. Many times they asked in exam. One is modified Euler's turbine equation. Second one is they won't ask directly degree of reaction. What they will do, they will ask you to, okay, I'll explain what I'll ask. I'll show you what is the question they'll ask. The next heading is, one is degree of reaction. One is utilization factor. It is defined as the ratio of energy utilized by the rotor to the energy supplied to the rotor. Again, this is also expressed in terms of different heads. What is that head? See here. Energy available is this. And energy utilized is this. If I make a ratio of that energy utilized by energy available, same equation I'll put. I'll cancel off the some terms and remaining I'll get like this. So this is called as utilization factor. It tells about the efficiency. How best the turbine is going to utilize the power supplied. Means or the energy supplied to generate the power. So this is the formula for utilization factor. And this is the formula for degree of reaction. He won't ask these two. But what he will ask is next heading. That is important. Yeah, this one he'll ask. You can see earlier question paper. In most of the question paper, they've asked you to derive the modified Euler's turbine equation and express the relation between degree of reaction and utilization factor. So many times they've asked. So what to do this? This is very simple. If you know degree of reaction, see this R formula from where I took the R formula from here. This is the R formula, right? R is that, and utilization factor is this. He is asking you to express the relation between those two. So what you will do? First, let me write R. Same thing I copied from above. Whatever is there, I written above. I copied here. And I have simplified this, means whatever is there in the numerator, I taken here and then I multiplied with R and it done with this equation. I got with this equation. Still, I taken the R common outside, then I got this equation. So finally, I got R in this form. Keep it aside. So from the degree of reaction, I got in this form. What is the reason I'm getting like this? Because I want to express degree of reaction in terms of utilization factor. Now we will go for utilization factor. Write down the utilization factor, whatever we got go in the above step, in the previous step here. Same thing I copied there. Same thing I reproduced here. You write this. Then you simplify this also. Or what you do is here, wherever there is a U1 square, U2 square, VR2 square, VR1 square. In this place, in place of this, you substitute like this. So that you are going to express the utilization factor in terms of degree of reaction. That's all. It's a very, very simple derivation. It is not a derivation we can call very basic. Write down the R, Write down the utilization factor separately. Then express U1 square, U2 square, and VR2 square minus VR1 square in the form of this. So wherever it is required in utilization factor, substitute this value. Simplify, you will get this. Utilization factor is equal to V1 square minus V2 square divided by V1 square minus R into V2 square. More than 10 to 15 times they have asked this question. Are you getting? Srivatsan and Vijay Kumar.
Yes.
So in this equation, in this module, you please write down, these are all the topics what he is going to cover or what he is going to ask. First is modified Euler's turbine equation. Then is the relationship between degree of reaction and utilization factor. Have we copied? Have we written that? This heading, so many times they've asked, relation between degree of reaction and utilization factor and that modified Euler's turbine equation. If you know those two, I think probably one question you can easily answer. Okay, na?
So cancel once again, sir. Degree of freedom.
One is relationship between degree of reaction and utilization factor.
Utilization, yes.
That is one question he's going to ask in exam many times. And the second question he may ask is derive an equation for modified Euler's turbine equation. Modified Euler's turbine equation. These two so many times they've asked.
Yes.
And this also asked, but not as he is asking though that modified Euler's turbine equation or this degree of reaction into the separator. This is also asked. Just this is a figure. What is the figure indicates? He will ask you to draw the different velocity triangles based on the value of R. It is based on the value of degree of reaction. Here, draw the velocity diagram for different values of R. Simply like this. You draw the different velocity diagrams for the values of R. So you can draw either this concept in this figure or this is simplest, means I have shown in only one figure, one sheet. So this is the generalized triangle. You know, for the steam turbine, this is the generalized triangle. If you write the heading like this, if R is greater than 0, if the value of degree of reaction is lesser than 0, or we can call it as negative. If R is less than 0 or R is negative, then what will happen? This is the condition. For this above triangle, you apply this condition. What is that? Inlet triangle should be big and outlet triangle should be small. See, where is inlet? This is inlet. So that try to draw inlet triangle bigger compared to the outlet. So this is the generalized triangle. This is not required. He will ask you to draw the different velocity triangles for various R. So this is R. R is equal to less than 0 or R is equal to negative. If R is equal to negative, you should satisfy this condition. Inlet triangle should be greater than outlet triangle. See here, inlet triangle is bigger than the outlet triangle. So then the turbine is called as impulse turbine. It will become as impulse turbine. Then, if R is equal to 0, what will happen? If the R is equal to 0, then inlet triangle should be little bit greater than outlet. Here it should be much more greater. Here it is little greater. So try to draw a little bit bigger compared to outlet triangle. And there is no friction in plates, energy transfer to the absolute kinetic energy. You can write this. And if R is equal to 0.5, then it will become Parsons turbine. That means what? You know the Parsons turbine or reaction turbine. Inlet triangle should look like outlet triangle. So for R is equal to 0.5. If R is equal to 1, then outlet should be bigger than the inlet. That is for pumps. If R is equal to greater than 1, then outlet should be very, very big compared to the inlet. That's all, very simple. See, if R is equal to less than 0, inlet should be big and outlet should be small. If R is equal to 0, inlet should be little bit big compared to outlet. If R is equal to 0.5, both inlet and outlet should be same. If R is equal to 1, outlet should be big compared to inlet, that is for pumps. And if R is equal to greater than 1, then outlet should be much more higher compared to inlet. Can you see how I changed the velocity triangle here? Same triangle, the same original triangle, whatever is there, I have considered for different R's. If R is equal to less than 0, inlet will become very, very big compared to outlet. R is equal to 0, inlet will become a little bit bigger than the outlet. If R is equal to 0.5, these two will become inlet and outlet will be same. That is symmetric. If R is equal to 1, outlet will be bigger and inlet will be small. And if R is equal to greater than 1, outlet will be much bigger than the inlet. Is it clear? First 3 is for turbines. R is equal to less than 0, is equal to 0, and 0.5. These 3 are corresponding to the turbines, because always inlet should be greater than outlet for the turbines, or it must be equal to the outlet. So that these 3 will satisfy for turbines. And if the outlet is bigger than the inlet, then they are corresponding to pumps. So these 2 are corresponding to pump, and these 3 are corresponding to turbines. Any doubts in this? Abhishek, Srivatsan, Vijay. See, why I'm concentrating on this more is because you can score good marks in this. Just by learning this drawing, this sheet, you can get 6 to 7 marks if you ask. They will ask for 6 to 7 marks. Draw the different velocity triangle for different values of R. Or any 3 they will ask. R is equal to negative, R is equal to positive, and R is equal to 0. Draw the velocity triangle. If it is negative, make inlet very, very bigger. If it is equal, then inlet should be a little bit bigger than outlet. And if it is positive, you try to make outlet bigger compared to the inlet. That's all. Positive corresponds to pump, negative corresponds to turbine. Is it clear?
Yes.
Hello? Okay. So next class, what I'll do, there are 3 more derivations in the next class. Those derivations are again taken from the velocity triangle only. I'll explain how to derive that. And after that class, I'll go for problems and I'll wind up this chapter. Is it clear? Hello?
When do you have next class, sir?
Next class, I'll take today last hour.
Okay.
I'll take last hour. Today's last hour, I'll take as next class. Still, if you attend 2 more class, you will come to know what exactly they are going to ask in the second module. They are going to ask modified Euler's turbine equation, Euler's turbine equation, degree of reaction, utilization factor, the relation between degree of reaction and utilization factor, and velocity triangle for different values of R. Okay, na?
Yes, yes.
See, you refer the earlier question paper for the module 2. You will come to know what only 3 to 4 common questions are there. Only within that 3 to 4 questions, you will get definitely anyone. Not much. Okay. Okay. So with this, I'll wind up this first class, the morning session class, that is 8:30 to 9:30. Again, I'll take the class from 11:50 to 12:50, last hour, as usual, my class. Okay. I'll share the notes in Google Classroom. You can copy the notes or you can read from there. Okay. Let's stop recording and again let us meet at 4th hour. Thank you.
Thank you.